Okay, so as promised, I have something special for you guys this week. So here we go. And okay, so here we go. So this is part 2. And so now we're going to see what we can do with polynomial growth. Okay, so this is ancient solutions to the heat equation. And now we're going to impose polynomial growth. And we're going to give it we're going to quantify it with a Q. So of order Q. All right. And what we're going to do, the reason why this is a little bit special is because we are going to slightly detour from the method and proof and paper, etc. of Lin and Zhang. And instead, what we're going to do, we're going to build on the estimates that Ben proved for the dimension of harmonic function of the space of harmonic functions with polynomial growth. So build on what Ben presented, and that's going to allow us to make to get a result that is we're going to get a result very quickly, and it's going to actually be a little bit better than what Lin and Zhang produced in the order of the estimate. It's, yeah, I'll make some remarks at the end, but and I really have to say that this is completely due to Ben. So Ben Andrews, in case someone who's watching doesn't know which Ben I'm talking about Ben Andrews. Okay. I think I told a little story about it last week, so I won't repeat the story. But yeah, this is Ben's proof. Okay, so we're just going to go straight. We're going to dive straight into it. I think the method is really direct and straightforward. Okay, so we're going to let U be in a space which we call AQ, which is ancient A for ancient, Q for polynomial growth with order Q. Okay, so I'll say ancient Q on M cross minus infinity 0. And we're going to assume that M has non-negative Ricci curvature. Okay, and then what we observe, okay, then Li-Yau implies, okay, so the Li-Yau differential Harnack inequality, the local version, implies that ut over u, and so we just discarded the gradient term, is greater or equal minus some universal constant divided by r squared. And here we should evaluate in a cylinder with radius r, centered at some point x. Okay, and yeah, I think everyone knows what that is, but I'll just write it down anyway. Okay. All right, anywho, so what this means is, I'll just use a different color, I guess, that ut is bounded by u times a constant, and then you've got this r to the minus 2. And what we did in the Lin and Zhang proof before was we used this, so we can at least compare with Lin and Zhang. We used this to show that the time derivative has a sign. And then we went on to the whole completely monotone thing, representation formula, whatever. But we can also observe that this equation, this estimate 1, implies that we have an improvement. So every time we take a time derivative, we improve our polynomial growth by 2. And note that if u grows slower than, oh, there's a chat. Oh, yeah. Thank you, Ben. Non-negative solutions. So ancient solutions with polynomial growth, and of course they should be non-negative. Thank you. Non-negative. Okay, so we're going to let u be in AQ, ancient Q, and these should also be u greater or equal 0. So yeah, thank you for that.
Glenn, I don't think we actually want to assume non-negative because we've got a Liouville theorem for non-negative things. So non-negative ancient things are constant. Yeah, so you have to do a little bit more of a trick here. The thing,
so
you can apply Li-Yau if you know it's non-negative on some set, and you get that from the polynomial growth.
Oh, right. Okay. So, okay, wait. So
you add a constant to make it non-negative if you know that it's
okay. Wait. Yes, you're right. I got confused.
Sorry. Yeah.
Yeah, I don't want to assume it's non-negative. Yeah. Okay. Yeah. So the step that I'm missing is because I think the step that I'm missing, Ben, please just correct me if I mess it up, is because u is smaller than 1 plus the distance from x to x0 plus square root t to the q. This is less than or equal to constant 1 plus r to the q. And then you have these shifts that I think is the point. U plus c times 1 plus r to the q, and c 1 plus r to the q, that's a q, minus u. These are non-negative solutions to the heat equation. Okay, so does that fix it? Oh, Ben's got a thumb up. Sorry, I wasn't looking at my screen. Does that fix it now?
Yeah, at least they're non-negative on the parabolic ball now, on the QR, right?
Yeah, okay,
yeah,
so
which is what
they're non-negative. And so now, so let's just, okay, so now let's just get back. Okay, so now Li-Yau. Yeah, sorry, that's actually an important point. And yeah, thank you. Okay, so now we go write this equation. Okay, now it's better. And now that we have this estimate, actually we can just replace this here and we get C, maybe a different C, a C twiddle, R to the Q minus 2. Okay, maybe that's better. I mean, that is better, but hopefully it's okay now. Okay, so let's try to fix this. No one will ever know, especially since this is definitely not recorded, right, Paul? It's all good. Okay. So now Li-Yau implies this, okay, and now we can say what I was trying to say before, which is that if U is in AQ, then UT, okay, it's automatically in AQ already because it satisfies the same PDE, but now it's in AQ minus 2, and if Q is less than 2, then UT is just 0. Okay. All right. So now you apply this to a number of to increasing number of time derivatives of u, and what you find is that if you differentiate in time enough, you get 0. And how much is enough? Well, it just depends on the polynomial growth that you were given before, the q, and you just divide by 2. Because every time you differentiate in time, you subtract 2 from the order. So what this means is that as a function of time, u is polynomial. Okay, and all right, so that means that we have a, formula for it. So let's finally use some arguments. Okay, and okay, I equals 0 to k minus 1, and okay, this is just a coefficient function of x only. And then we should do this, and we'll just divide by I factorial, so that when we differentiate with respect to t, we're going to be shifting coefficients to the left. So, all right, let's give this a number. So differentiating 1 with respect to t just deletes the lowest order term and then moves all the others to the left. So moves coefficients left. And differentiating, if I could write, it'd be good. One with respect to x factors through. So what does that mean? It means that if we take, because u satisfies the heat equation, so ddt minus Laplace u is 0, and that means that the Laplacian of the highest order term, right, because of just equating coefficients, has to be 0. And it factors through all of the remaining terms as well. And it means that, for example, the Laplacian of uk minus 2 is the Laplacian, is uk minus 1. Okay, and so if you do an extra Laplacian, then you will get 0. Okay, anyway, and so on. Okay, by the way, this is the second part of Lin Zhang's theorem 2. Theorem 2.1, I think. All right. So that's the polynomial representation, but what about the dimension bound? The dimension bound is going to, okay, so let's talk about the dimension bound. So because the Laplacian of uk minus 1 is 0, it's harmonic, and that means that it's in HQ because of the growth condition. The dimension bound follows, well, let's not say the dimension bound, say for the dimension bound. For the dimension bound, observe that uk minus 1 is in this space HQ, harmonic functions with polynomial growth of order Q, and the dimension of HQ is bounded by a constant, depending on n, and q to the n minus 1. And keep in mind that the expression obtained by Lin and Chang is like a constant times q to the n plus 1. Okay, so this n minus 1 is sort of 2 orders in the exponent, so are better. And we're going to lose 1 order in a second, but we're not going to lose 2. Okay, and now what about uk minus 2? Because Laplacian of uk minus 2 is uk minus 1, and uk minus 2 is has growth 2 orders less. So what this means, okay, is that if we solve this equation, say given a particular solution, like a u twiddle k minus 2, the solution space, right? Because this is just an inhomogeneity. This is just like the Poisson equation. It doesn't actually change the dimension of the solution space usually. Solution space is spanned by this u tilde k minus 2 and some harmonic function. And because of the growth, the harmonic function is going to be in HQ minus 2. Just like that. And this goes all the way down to U0. So what that means is that the dimension of AQ should be bounded by a constant, depending on n, and then we have to add up all of these different dimensions. We're going to get q to the n minus 1 for the first term, and then we're going to get q minus 2 to the n minus 1 for the second term, and so on. It's going to keep going. N minus 1, and we have to add these things up a bunch of times, whatever the last one's going to be, minus 2k minus 2 or something, plus 2 or something, I guess, n minus 1. And okay, that's bounded in general, no matter what k is, it's bounded in general by some c hat n q to the n. And that's it. That's it. Yeah, so I don't know, 10, 15 minutes. Did I miss something, Ben?
No, that's good. Yeah.
Yeah, just forgive my stuff up with the non-negative stuff. The non-negative you need for Li-Yau, and you need to apply it to an associated function. Yeah, sorry about that. Oh, maybe some comments. This requires non-negative Ricci. I don't think, I mean, I guess you could try to use a different type of Harnack inequality that would apply for more general manifold, but at least the argument here needs non-negative Ricci. And at least in the Lin and Zhang's paper, they have a remark about more general spaces. So maybe Ben might want to say a few words about adapting this to more general spaces, but I suppose their technique might be better for that setting.
I think, sure. I mean, I think there's lots of situations where you can't use this trick. Everything we did here depended on being able to differentiate in T and still get a harmonic function. So as soon as you have, for example, time varying metrics or that sort of thing, then that won't work. So it's still useful to have the Lin-Zhang argument, I think. But this works nicely when you have, for example, a product structure of some sort.
Right. Cool. Yeah.
Yeah, I'm not sure why Lin-Zhang miss out the extra power.
I don't know if their argument can be improved or if it's an essential kind of restriction. I don't know.
Yeah.
Okay. So yeah. And u of x and t equals sum I equals 0 to k minus 1. Yeah, I'm just writing the theorem, but if people want to talk, just talk. What is this? I factorial. And then t to the I. And so what's the rule? Laplacian of u I equals u I plus 1. And Laplacian of u k minus 1 equals 0. I think that's it. So yeah, if there are no questions, then I guess I'm done.